essentially a build out of half of this fourth floor coupled to something called Practice Point in medical robotics, which is the other side of the house. And then the other thing is I always say it takes 3 years to notice any differences, but we started this in 2016, got awarded in January of 2018. And then now we find ourselves 6 years later, but in the meantime, we actually hosted the same event. And this is on auto, it's trying to keep me moving forward. Is there anybody here that was here during that session? And do you recall anything that was here or not here? There's like we toured this space and it was empty. So we had just moved in, every room was empty except maybe a few things. I think we had one instrument in. So here we are, 2024. 6 years makes a big difference, and so we'll have some tours afterward and stuff like that. So we're really happy to be here. And then I'll just go into my pitch, and I'm going to make this really short, and then Pratap can do the flexible electronics pitch. But the integrated photonics, I have one that I can pass around. Maybe not. This is an odd shaped thing right here. And everything gets manufactured in RF SUNY in Albany at their fabrication facility. This has some lint, so could you take off the lint and then pass it around? But there's a chip in there. And what we were set up to do is do testing and characterization. And there's a pic down there, and then you see Owen and the graduate student Jose working on the probe stations in this facility. And so the whole idea is chips get made, we test them to see how they're doing. Charlie is here, who just submitted his senior project today, working with. I haven't spent the grades yet. Oh, we can bring that up and do group grading. Good audience. And so we were working with Spark Photonics, and so this is just some of the projects we have going on. And so this is the chip that's being sent around. Yeah, there's somebody up there that is in the room that's also on. Actually, both of you separated by. So here's Caitlin. Oh. Caitlin and Charlie. So, and Charlie was actually being mentored by Caitlin at the time, who was trying to do, and he graduated. Good job on mentoring. There's a clean room. We have NanoScribe where we can put lenses on the end of fiber optics. We do a lot of outreach, and I was going to say that with this project, Spark Photonics is actually making the chip designs for AIM Photonics that customers would then use. And so Charlie and Max actually found several nuances to the first design that's a wonderful feedback into the Spark process. And the Spark Photonics was the previous speaker, Kevin McCumber, who started Spark Photonics, was the previous speaker, I think, last month. And so there's a good connection here. But we have a lot of partners in the sort of research and development space, doing a lot of measurements. I don't want to go into that because we're all from different disciplines. But the part that you're probably interested in and is relevant, Caitlin's one of the wonderful examples, is the photonics talent pipeline. And so we do this in an integrated sense. We have PhD students, we have undergraduates, the MQP students, that's the senior projects. Charlie came in as a sophomore or freshman, and a lot of students I think he came in as a senior MQP, I think, yeah. Right? And so they come in a lot of different pathways. So we don't talk about a pipeline, but we talk about pathways. We're also coupled to QCC. And so that's something everyone's interested in, is the talent pipeline. So I'll focus on that. So you saw the posters, and this is just a collage of photos. Do I have any equations? Oh my gosh. I don't have any equations. There's actually an equation right here. You can all focus on. But the part of that is we're having a poster session. Luba Titoba, who's actually in our office right now that you might have seen, runs a poster session for local community colleges to and encourage the students to transfer. from QCC, Mount Wachusett, and other places. And so that's a big push, and we try to get them exposed to the project-based learning mentality that we have at WPI. And so that's what some of the posters are out there for. This is just a slide saying we do projects. We take courses to support the projects. And there's a map. Every year there's another project that students take. And it ends with the major qualifying project, which is a year-long project. And we've had symposiums before with, this was a collage of different students from Stonehill and Quinsig and at various places. And then our photos, and then my son now teaches high school. Oh, where is he? It's a little blurry. Anyway.
You're one of those kids.
Yeah, I'm doing the back. We also do manufacturing mashups, so you'll recognize some folks on that. So we do a lot of outreach to spread the word. This is the Quinsigamond Community College partners, and so we've actually hosted students here. We go to their location, and we just signed, the two presidents just got together this week and signed a transfer agreement, which goes beyond just what courses you count, but also to support programming and pathways into programs. So it's a much more meaningful agreement than just saying what courses you're going to count. And so we really appreciate the faculty at QCC and that growing partnership. We've also had this very room, we've had alumni come back. So this is AIM Photonics coming out to give updates on what they're doing in Albany. And you recognize the back of his, oh, he's not here, that's right. That's Max, Charlie's partner in crime. But one of the presenters was a student that came through LEAP that decided wanted to go to graduate school in May, which those that go to graduate school, that's not the time to decide when you're a senior in May that you want to go to graduate school. And we were able to get, Jim and I talked to AIM Photonics. Within a week, they had an internship set up for him. He was supposed to come back for graduate school. He's now a photonics engineer at AIM Photonics. Gabriel Dan was another one of our connections. We go down to the Worcester Public Schools. So Spark Photonics has a foundation arm that focuses on K through 12 communities. And so we had Spark Alpha, which is a kind of like a value creation entrepreneurship program in high schools, and they go around the state of Massachusetts and even further. We coupled off of that, and there's most of the public schools in Massachusetts have some kind of internship program, and this was coming out of the pandemic, and so it was harder for companies to sponsor students. So we had 8 interns from this group also come here with some daily activities. And so you can see some of the photos working on some basic skills and stuff like that in here. I think it's 3 of them ended up coming to WPI.
3 at WPI, 1 at QCC that will be public.
Right. And so we really try to create additional pathways and get students exposed to what they don't know, stuff like that. And then these are some more photos. There's also Girls Inc. of Worcester that Luba Titoba helps run those camps, and there's usually two photonics-based one each summer. We also have a research experience for teachers, where teachers get paid to come and do research during the academic year. And so that's another multiplicative factor. And if I talk about my son, so he's teaching in Beverly High School, and said, you know, I have this student, she's wonderful, she needs an internship, she's in Beverly. So she came out the last 2 days, and some of the integrated photonics have Mach Zinders interferometers, for those of you know those components. And I once tried to create, there's a Mach Zinder back on this optical table. And so it just splits the beam into 2 paths, recombines it, and you get an interference pattern. But because it splits it in the way it does, you have so many degrees of freedom to align that can go wrong, and you get steered down a rabbit hole, and it's something you can't recover from. So the student, 2 mornings this week, in about 3 or 4 hours of time, she already had an awareness of optical components. And for those in optics, just had the sense, and I just went through this once, just like, you know, I'm in here frantically this morning trying to do some stuff. Optic got caught on my sleeve. I stopped, of course, because I have the good awareness of mine. Then she just gently took it, laid it back down, right? But she was able, so that's a now working Mach Zehnder interferometer that a high school student put together in 3 hours with no previous training. And so this is where I was mentioning to some folks, she's ready to work with somebody in industry right now, in my opinion. There's right. And so we're also aware of things like that. So come to us when you have internship programs and stuff like that. And there will be students that are just really hungry for that. And also in terms of project-based learning at WPI, I've been here since 2016, and this is the biggest year where I have first and second year students begging for research opportunities and just wanting to volunteer in the labs. And so I think they've come out of the pandemic. I don't know if we have. I at first thought we would come out of it and it'd be symmetric for us because we knew what it was like before. I thought, oh, it'll just be a symmetric function, and it's asymmetric for the students because they don't know what it was like before. But now they're way ahead of us, I think. They're really hungry for engagement and stuff like that. So just keep that in mind. We can have a pretty good pipeline of both the technology aspects and the workforce aspects. This is I think a familiar poster session for many in the room, right? So Jim, I think that in 2 weeks there's another 12 days and 12 days, 4 hours and 13 minutes.
Not that Harvey County.
And then this is just some more photos of some equipment we have. I won't go too deep into that. We can do, I'd rather walk and talk after this session, something like that. And then some of our pro stations in the rooms and stuff like that. It's pretty cool. So there's a pick that has a red laser running through it. So it's lighting up. It's a spiral. And so it spirals in, and it's for measuring waveguide losses. But it's pretty neat to see. And so while the student was able to have a quick sense of mind on mechanical things that you can hold and feel and scratch and know you're scratching it, starting to work with small is another level, right? So there you can jam a fiber optic into a pick, watch it. Oh, this is the good stuff. Watch it blow up. And so this is, I actually showed this in an AAPT meeting. So this is Caitlin and Charlie again. And Caitlin in her LinkedIn page. Now the timing's working out. I didn't know it was going to be this. So we're so proud of her, all she's done so quickly and stuff like that. So
Good job.
I think there's one more. January 22, and you graduated, I think, less than 12 months before that.
Yeah, it was like 6 months.
Great. And then here's the I am Photonics, which is really cool.
Big story behind that.
I bet. Probably took a long time to get to that name, right? Yep.
That factory in North Andover,
Yes,
that's where I grew up.
yeah.
I had no idea.
Yeah, we're right behind the stop shop.
Oh, wow. I lived like, or lived 3 minutes.
Well, that's visit us.
I know. I live here.
Not far, they just came. So any questions? I was ready to hand it off, and then we can get back to conversations and tours and stuff like that. But if you have any questions, we can.
If I'm a company and I want to hire emerging talent, how do I approach you? How do I work with you to get the emerging talent into my company?
Yeah, so the stuff that's, I always find the timings are the biggest differences, right? And so most of our students graduate in May. And I think the ramp is we have the career days where companies can either come in and have tables and recruit students there in a holistic way. But then you can also just, I think, contacting, probably starting with department heads, and if you have a very specific discipline. So rather than going for the sort of global catch everything, you can also reach out to department heads and try to, I think that's probably the best, I think, point of contact. So this is a good question, because we have the career center and we interface with them. They do tracking, but they're kind of autonomous because they're really outward facing and want to bring people in. And of course, we send our students to that and prep them for that. But it's two or three events a year, I think. And so that's it. So then they're, oh, 3? Yep, 2. So 2 events a year. And they're packed. I think they turn people away that want to have tables and stuff like that. And so early on, Jim and I were also thinking to have something like that here at the LEAP facility. And so in some cases, there are students here, but we didn't collectively promote that this time, stuff like that. So we're open to doing things like that and just contacting us. But,
Would
and
that
then,
be of
the-
interest or value to companies? Okay, that's rude.
yeah, that's a good question. So is that something that, we get taxed a lot, everyone showed up for this, but then probably coupling something like this to a student poster session, which is going on tomorrow. And everyone's so busy, and Jim and I were talking, it's like, we should probably combine these two events somehow a little bit. So that's why actually we put up the posters out there, is that those are student posters right now. And we said, well, the middle ground is rather than making all the students come to two events, let's just have their posters up now, stuff like that. Other questions?
That is a good idea.
Yeah, so, and that's where, IMAPs and the symposiums, but there's always timing and it's just the amount of time, right? Does the student go to every event? Do you guys come every event? Stuff like that. So that's the thing. I don't quite know the right answer. So, but that's where, I think it's been more the coincidences, like, Morgan, what's that? Morgan Kaler. I was gonna say Caleb. Yeah, that's the #1 draft night, baby. Other things on it. Skillers draft yet? So we were at a meeting for the LEAP facilities, which is one of this, and we said, this is our first student that completed a project. And with integrated photonics, she now is a photonics engineer at MIT Lincoln Lab. And so it's more of these coincidental things and networking, which I think is usually the most effective way. So I wish there were another more efficient way, but I think it comes down to networking and timing.
Doug, I don't think it's any more grassroots than this right here.
Yeah.
Is your funding from the federal government?
Yeah, so part of the space is academic space, so we just get supported by that.
Right.
We do student
Universities
projects,
give you that.
so that's our bread and butter. Most of the other funding that funds both of us is federal funding. We do contracts with companies. We didn't do the normal pitch, but we are a user facility, so you can use the instrumentation at an hourly rate. The thing that didn't go the way we thought it would is we thought people would come in and use the instruments, the lovely high-tech instruments. They don't have the people to do it. So this is what Oregon was supported on 2 external, I think one was hourly, they're more like pseudo contracts. It was like, we have this work to do, we'll pay this much. So there were like small contracts it was like 25, 50K, 25K.
That brand, we had her for the summer and she was doing.
25K contract, they needed pick measurements made, didn't have the people to send here to do it. So she made the measurements for a company. They paid us 25K, that paid her. We thought she might end up with that company, but then she ended up with MIT Lincoln Lab. So we have things from hourly, come in and use the facility. We have assisted rates, and like Owen is now full-time, so he's an expert, but we have other students that make measurements. I have never made one. I watch. Oh, that's interesting. The pick lights up when you put red light in. And then we have then we have larger national collaborations for congressional efforts, where there's one with we're partnered with UMBC and a couple of companies, and that's through Army Research Lab, Integra, Vico, and stuff like that. UMBC, University of Arizona, UC Irvine, and a really major effort in that sense, and that's for ARL. So it spans the whole range from hourly all the way to bigger contracts.
What's UMBC?
Oh, University of Maryland, Baltimore County. Yeah. So
Just curious, I'm from Irvine. What do you do with UCI, University?
it is
The integration of MEMS and
He-
gyroscopes
yeah,
into PICs.
yeah, I can't remember his name right now. Sir
Andre.
Yeah. So Andre does MEMS devices, but he integrated, and so with MEMS device, vibrometry and gyroscopes and stuff like that, and detecting the movement's important. So he integrated a PIC interferometer to measure the small displacements, then be able to do the readout for the motion and stuff like that. But the more holistic thing was, packaging is a big deal right now with integrated photonics, and coupling it to MEMS and stuff like that And so that was also another part of the picture was, this is for navigation to denied environments and having MEMS devices. And then our side of it, UMBC and AIM Photonics is micro ring resonators to frequency cones for clocks. So you have a clock to be able to keep timing, very precise timing while you're GPS denied. And so there's a whole bunch, there's somebody else doing LiDAR for, not LiDAR, but laser communications, stuff like that on the field. So it's a very big program.
What department? Just curious, you know?
He's an ECE, I'm pretty sure. Yeah, it's an ECE thing. Yeah, I can get you the name.
I'm trying to piece this together and dovetail, talk a little bit about the marine resonators. What is some of the work that you're doing with NRL, et cetera?
Yeah, so that's so this is the ultra low loss silicon nitride platform. So that's actually, Charlie, do you want to get up and give a talk? He just gave it. So it's looking at the fundamental circuits for ultra low loss silicon nitride with low fluorescence for chemical sensing platforms, and also just developing up that platform in general. And so that's the NRL one.
Very cool.
And then the first student I graduated from with a PhD here is now a postdoc, NRC postdoc fellow in that lab. And then it's the end of the year, so I'm not going, but Jim and Owen are going down on Monday and meeting with them and stuff like that on the project. Jake Bouchard, yeah. Which many of you might have seen. He's probably yeah, so all the students are landing in places. So we're happy to have him in NRL for the continued collaboration.
How many students are in the program now?
You know, we thought about trying to do that calculation, at least Jim and I have. I mean, we must have 30, 40, 50 students on this side.
Yeah.
At any one time. So that's a good question, because from high school students to first year students to PhD students to postdocs, I'd say it pushes 60 in a year. And so that's holistic on this whole floor, because we have, I think I don't know if I had the one slide. So it's myself in physics and ECE appointment for Francesca Bernardi, who's a mathematician that does experiments. So she does microfluidics. So she has a little lab space, and the math department's like, oh, we don't have, what's a lab? Computer lab? A what lab? What? Luba Titova, who's over there, who does materials. She does mobility and semiconductors and carrier mobility, ultra fast, broadband spectroscopy of semiconductors and nanomaterials. We have Sean Liu that does fiber optics and sensing systems with fiber optics for a wide range of applications. That's mechanical engineering. I won't try to describe her top. Did I do okay with the other ones?
Yeah, you did.
Okay, good. I don't know what he does. I'll have to explain it himself.
Yeah.
So we're very interdisciplinary, and so collectively we just have a lot of students in the program. And so then you have to like say, well, what part of the program are you talking about?
Yeah.
But we're pretty busy.
Thank you.
At least after 10 a.m. we're pretty busy. Very good. And then things just came to, I mean, the timing of everything. So Luba, her experiment, a pump probe, ultra fast, ultra wideband spectroscopy system. She submitted a $500,000 grant to the NSF. And I think, did we move the table in before she got the award?
Yes.
So we're like, she does really well. So, and then there's a slide where we're bringing optical tables in through the 4th floor window at the end of the hallway. So we brought that one in and we didn't jinx her. So she still got the award. And then likewise, the NextFlex that Tom's going to talk about was just a super synergistic effort, all just wonderfully timed and stuff like that. So we're pretty lucky in that regard.
Oh,
Oh, can I have your cookie?
You can, I was breaking pieces off of it, so I didn't take a bite out of it, so go ahead. All right, so, yeah, I'm gonna switch gears a little bit, talk about the other kind of, work that we do here that's co-located with the photonics, which is the printed electronics, essentially, so printed, flexible, and stretchable electronics and sensors. And just like the photonics work was, comes out of AIM Photonics, NextFlex is another Manufacturing USA Institute consortium that's DoD funded, primarily Air Force, and another consortium, Semi-Flex Tech, which gets funding from mostly ARL. So the kind of thing that these folks are interested in is, shown in the picture there, basically highly flexible and even stretchable electronics. And so, how is this different than sort of regular flex PCBs? It's all additive, and they're actually thinning down the bare die. So your ICs are unpackaged ICs that are actually thinned down in some cases to below 50 microns, where the silicon itself is flexible. And then you do flip chip bonding onto a flexible substrate, and then you package the whole thing. So it's sort of ultra low cost, thin and light, and very, very application dependent packaging. So for that, what's shown there is they have a flexible microcontroller, sort of a generic like Arduino type microcontroller that you can get from them and plug it into whatever application you have, be it wearable devices or whatever else. So this is one of their fab is out in San Jose, California, and they have a full line of printing and assembly tools out there. They're also looking at kind of environmental benefits of doing additive versus subtractive technologies to make the circuit board. So you're actually printing the conductors additively, right? So you're not etching away a bunch of copper and creating lots of hazardous waste. And these guys are looking to play in the sort of CHIPS Act when it comes to heterogeneous integration and packaging. So doing heterogeneous integration and packaging with additive processes. So this is just a cartoon showing the types of things that they work on. So you're still placing ICs. But you are printing things like your actual circuits are being printed, you're printing displays, you're printing antennas, and trying to make the whole thing flexible. And these are just some of the areas that are of interest. So they have what are called technical working groups. So they split them off into human machine interfaces, health monitoring, structural monitoring, mainly for aerospace, industrial, chemical, monitoring. So those are all some application areas that they're interested in. So what we did at LEAP here is that we basically have brought in a bunch of different printing methods, which will show inkjet printing, screen printing, and micro dispense printing, but of conductive materials, of functional materials to actually build up circuits. And in addition to the printers, we also have rheology, particle sizing, contact angle, things like that to develop the inks. We have a flip chip placer bonder, a fine tech instrument that we use to do flip chip bonding, and then test equipment for flexing and stretching these circuits, and measuring them while we do that. And so I'm just going to run through like a couple of example projects just so you get a flavor of what kind of thing that we do. So this was an example where we were trying to miniaturize basically circuits printed by inkjet. So these are all silver nanoparticle inks that we're printing, and we're trying to see by changing the jetting frequency and the temperature, can we get really, really narrow, high aspect ratio traces so we could print miniaturized circuits. So, so what we found here is like basically if you crank up the temperature of the surface on which you're printing, you can get the ink to do what's called pinning, basically before it lands and the edges get pinned before it spreads out, and you can really confine the ink to be a nice high aspect ratio trace. And we worked with some folks from Carpe Diem Technologies. Probably a lot of you know them. They do nano imprint lithography for roll-to-roll nano imprint lithography with lots of applications in photonics as well. But we use their nano imprint lithography to basically make a print surface that had all these micro pillars on it. And if you print on the flat surface, you know, the ink just goes everywhere. But if you print onto these pillars, you can get the ink to pin in, you know, nice rows and columns and get very nice straight edges that are even narrower than printing on a bare surface. And then we also kind of push the inkjet printing to like its ultimate limit, basically, where we printed on a really high contact angle surface. So this is capped on with a fluoropolymer coating. If you just print on it, the ink absolutely will just bead up. You can't even print lines. So what we did was, where you see the dots, we actually printed separate dots of ink and then let that dry, and then actually printed bridges in between, where the bridges would wet the posts kind of, and you can print an inkjet line that's, you know, 12 microns in width. So this is some of the stuff we were working on, funded by NextFlex, and their whole angle was, you know, this is the circuit that they have for their flexible microcontroller. And the way they're making this is a two-step process. They come in with screen printing of silver ink. And then that works very well for most of the circuit, you know, where you're putting passives, and then this is your connector part. But for the actual die attach section, where they have the bare die flip chip bonded onto the printed circuit, they needed a much higher resolution. So they came in with a second process of laser micromachining to improve the resolution of the screen printing. So what we did was show that you can do that in one step with the inkjet, the high resolution inkjet printing of very fine lines. So this is the bitmap of the die attach pattern, and that's the inkjet printed pattern. And so this work was done by Nick Pratt, now Nick Pratt PhD. He graduated and is working for SI2, which is now Antenna Research Associate in Billerica. And then, so that was flexible but not stretchable, right? So we also do stretchable electronics, which is basically printing inks that are metal polymer composites. So, you know, you print them, you cure them, and they are stretchable composites. And so this was a human machine interface where we actually printed a whole glove and sleeve that had sensors all over it, and then a pneumatic layer on top that, so that the sensors track your fingers and arm motion, and you can control a robotic arm, and then the pneumatic layer provides force feedback from the robotic gripper back to your hand. So you can feel what the robot's feeling. This is what it looks like. So all of these are stretchable silver polymer composites that are screen printed, and then these are all, you know, the flex boards, those kinds of FHEs that I was showing you, flexible hybrid electronics, that are, you know, where there's a chip that's reading out these 4 strain sensors on that board, and that's an example of, that's Ritwik in the back. He's picking up some random object. I don't know what it is, but yeah, there you go. All right. So yeah, so the reason this work is interesting, like, you know, if you look at the elbow of this thing, right? So the strains go up to like 40–50% right there. So you have to be able to get a signal and power all the way from the shoulder to the arm, right? With the elbow flexing, you know, and so we put this through, you know, 1,000 cycles at 40% stretch, and have to make sure that the total resistance doesn't exceed some critical value. We also, well, okay, let me go back. So the main place where this fails is right here, right where the flex board connects to the stretchable traces. So the flex is, you know, polyamide, and then the stretch is on a stretchable TPU. So right there where you have the conductive adhesive, that's where.
So
Yeah.
has it failed when you had the arm on, and what does the robot do when it fails? Is it like
The
all of a sudden an uppercut?
The robot goes like this.
Oh, okay.
I have to do this.
Thought it would be more dramatic.
So yeah, so what we imagine wanting to make this stretchable as well, that the flexible board, make that stretchable as well. So working with a company called UES out of Dayton, Ohio, they're right next to Air Force Research Labs, and they commercialized this gallium indium eutectic, printable liquid metal that came out of Air Force research labs. And so we're printing that onto a stretchable substrate and encapsulating it so that it's essentially a liquid metal confined within a TPU channel sandwich kind of thing. And you can actually stretch this out to 225% strain for 200 cycles, and then do it all over again and get, very, very minimal resistance. So this is a 5 centimeter long trace, right? So it starts out at, a less than an ohm. You can put it through this ridiculous cycling, and then you do it all over again, and the resistance hasn't really increased much. So you can get a fully stretchable circuit that way. You're shown vias and component attached. This is just, so that's the straight line. That's a line with a via going from one layer to another, and that's a 0 ohm resistor component placed in there. And you can do things like this. This is a little demo circuit we made, just some LEDs where you have, some of the LEDs in the bottom layer, some in the top layer, and it's a fully stretchable circuit. So where we're going with this is, these were made with so-called direct ink ray, which is a nozzle printing the ink. Really good for prototyping. Then once you know what you want, you can go and get a screen made, and you can switch to screen printing of the same thing. So that's kind of your prototyping to volume manufacturing. And so next with this, we're going to go, to finer traces and actually do some packaged chips and things like that, and try to make, more functional circuits. And then one example with the other side of the house here that's doing the medical robotics, Professor Pichera. He's in the robotics engineering department at WPI. So he has this interesting project on vocal cord laser surgery, where you have an endoscope that's going into the person's larynx, and then there's the optical fibers going in, and there's good ways for people to do shape sensing of the whole endoscope now with like things like the continuous fiber Bragg gratings. But right at the very tip of the where the fiber comes out, there's this little guy here, which is called a notch wrist tube, and it's a little continuum robot that is doing the last stage of fiber guidance. And this thing currently, the way they're doing it is just it's just being driven by a cable. So you pull the cable and it bends, right? And so if there's any friction or it's touching anything else in the larynx, you can't tell just by how much you pull the cable what the curvature of it is. You can tell the average curvature, but the end might be kinked or whatever, right? So we want to actually put sensors on the tip of this thing to like actually all along the spine to measure the local shape. So this was again printing that liquid metal in the shape of a little strain sensor and adhering it onto the spine of this little notch wrist tube. You only have about 1 millimeter of space. So the spine is 1 millimeter, and then this whole thing is 2 centimeters, something like that. And so what we showed was basically you can get a very, very repeatable and reliable strain sensor. So you're getting strain all the way up to 10%, right? So you can't use a regular metallic strain sensor. They only go up to 1%. So you need to be able to go up to 10% strain, but have absolutely 0 drift, right? So if you have a polymer in there, any kind of polymer, metal composite that's conductive, the polymer is going to undergo drift and hysteresis, and you're going to get resistance gradually increasing over time, which is what happens in regular composites. But this liquid metal stuff can give you this totally repeatable, strain gauge behavior, and it can fit on the tip of that tiny little notch wrist tube. So that's kind of an example of a collaboration with the guys next door. And then, yeah, we also do some fun courses. So I did a printed electronics and sensors course this past term. And this was a collaboration with Professor John McNeil from our ECE department. He has this, he calls it the PUP system. It's the pressure ulcer prevention system. It's a soft pressure sensor that is used to prevent bed sores by, you put it on a bed or you put it on the patient so that you can detect pressure has been too long for a certain amount of time. So students basically printed these spiral types of pressure sensors and then put weights on them to figure out, what their response was. And then we we took all the different people's sensors that they made and plotted them together and then looked at, hysteresis and drift and noise and all the good stuff that you look at when you look at sensors, linearity. So they enjoyed that a lot and learned quite a bit from it. I think that's all I had. It was a graduate course, but at WPI, when you offer a graduate course, you have all the undergrads that came in that were already juniors because they have so much advanced placement credits. So they show up, they're pretty much juniors already. And then you offer a graduate course and you get first years. So it was a grad course, but there was there was a mixture of undergrads and grads for sure. Yeah.
Interesting. Is that a common occurrence here?
Yeah.
Very common. Yeah. So they're able to finish a bachelor's and master's very often in 4 years.
Right.
Yeah.
Okay. 3+1.
3 years even.
We started as a 4+1 and it ended up being 3+1 for a little
Yeah.
bit. And it's the AP credit coming in calc already and physics.
Yeah.
Physics, calc, and some humanities already done. So.
Yeah. So if anyone wants to know more, yeah. Or
Like one of in the first couple of slides, you said on the flexible circuits that you had dye that you thin down to 50 micron.
yeah.
Maybe it's because it's so thin that it's so flexible, but how do you handle 50 micron dye? That seems.
Right. So I mean, I don't, but next one. Yeah, I mean, they've developed a pick and place line based off of the Universal Instruments pick and place machine that was designed specifically for this. So they have that in-house at their fab. And I don't know how different it is than conventional die handling, but they're doing it at, not high volume, but they're doing it at least mid volume. Yeah,
Do they just polish it down to get it thin?
they do. Yeah. Yep. So that's I believe the main processor on this is a Nordic, and so Nordic does that and sends that to them. And they have other sensor ones that they're using from Analog Devices. So they do the thinning down. Yeah,
My mind is being blown. I'm being introduced to flexible conformal electronics. How environmentally robust are these?
Yeah. Well, so basically, so NextFlex is not only they not only have their own shop, but they have project calls regularly being put out there. And one of the main topics in the project calls is basically like leading edge electronics, like think like hypersonic vehicle leading edge sensors, right? So they have some of the projects they're running are temperature requirements out to some ridiculous values, and they are they're doing this type of packaging to satisfy those types of requirements. So I mean I think they're getting very, very good at it, basically, where you can make these very robust.
So for the current state of the art, I mean, have these been environmentally qualified beyond these like very extreme temperatures, et cetera?
Yeah, they're always working on it. They're always doing it, but there's yeah, I could get you a specific answer as to what extent that has been done. I don't know off the top of my head. Yeah.
Thank you.
Yeah.
Interesting to see the ICs at 50 microns, but obviously it's a lot of extra processing to take a conventional IC and motion down to that.
Yeah.
Is there any interest in or research into, wafer fab? Why don't you make it this thin instead of making it?
Yeah. Right. Yeah, so what I'm seeing is that there's a couple of companies that are essentially making they're using fab equipment from sort of 2 generations ago to directly do basically thin film transistor ICs, right? Directly on polyimide. So like there's a company out in the UK, I'm blanking on the name, that is doing this at scale. So it's a couple of nodes back, but it's not on silicon, but they're, you know, I think that is something
We do
that's,
it today for like displays and.
Yeah.
Certain types of technologies.
that's a good point,
Not
yeah,
necessarily like conventional ICs.
yeah. I think there's definitely, you know, some room for that, yeah.
Just to clarify, the picture you're showing is, that's polyimide, not silicon, right?
That's polyimide, yeah, right. But the, where is it? I mean,
Those squares.
yeah, so actually, you know where it is, like,
The features are on the silicon.
this right here is the thin silicon die on this.
Okay.
And it looks a little bit shiny because of the encapsulation, but yeah, that's the
So
silicon.
that's the polyimide is concentrated.
The polyimide is on the bottom, and the top is actually, in this case, it's, some sort of a TPU and, over the top, yeah. Yeah. Yeah.
It sounded like you had said that when you deposit the metal ink and you raise the temperature, it flowed less? Is that what you said? You called it pinning. Is that
yeah.
because of some evaporation of a solvent? Because you would typically
Yeah.
think the higher energy is going to spread.
No, that's right. So, yeah, in that particular case, yeah, in this case, so it's an ink that's like heavily loaded with the silver nanoparticles, right? So you get faster evaporation from the edges, and then it forms a little solid barrier essentially there. Yeah, that's right. It's because of the evaporation. Yeah.
When you make these on such thin materials, do you have any limitations because of the problem with getting the heat out?
You mean when they're in the actual operation?
And when it's an operation?
Yeah, no, that's a very good point. I mean, so, you know, they are restricted in terms of power, you know, you can't run. So, I mean, again, a lot of the work, that they're doing is to improve, you know, sort of higher aspect ratios, materials, so you can get a lot of cross-sectional area, right? You know, the work we did on inkjet, it's not the best for that. Ink, you know, even if you do pin the traces really narrow, these are just like a micron thick. But some of the work with the direct ink write and some of the other additive processes, you can get, you know, some nice thick traces that can really handle some power. Yeah.
On the robot elbow, you
Yeah.
showed the traces going across the elbow. Are you actually measuring things on the elbow itself, or is that just for sending signal?
Yeah, no, good question. No, so the whole trick is that it's just for sending signals. So whatever you're measuring, so we're actually measuring, these are, you know, capacitive strain sensors. So you want to digitize that as close to the sensor as you can. So this has been digitized, and now it's being sent down here as just, you know, serial data. So it's very insensitive to whatever's going on over here. Yeah.
My follow-up question.
Yeah.
This is Optica. Have you thought about using, instead of those thin strings, using some sort of
Optical, yeah. You know, you could, I mean, it's a good point, yeah. There's another manufacturing institute that's called APOA, which is actually based out of Cambridge. Yeah. Which you all know about, but I mean, they are basically, you know, putting fibers into the textile itself, so that is definitely like a good alternative approach, yeah. Yeah.
Can you inkjet print optically transparent materials? You know, like
Yeah.
tin oxide is the obvious thing, but that shouldn't have a temperature. But are there other polymers and things that you can inkjet print that you would light down?
Yeah, so we currently print SU8, you know, a photopolymer, in the same inkjet print head. So not literally the same print head, but the same type of print head. And I think Milica has a poster out there where we're doing multi-layer inkjet, you know, silver SU8 layers. And yeah, I mean, that's optically transparent, and it's a little bit of a lossy material, but if you care about that, but yeah, you can print dielectric, yeah.
Have you done any work, or does it make sense, like, for a photopolymer for like a SLS type of application, either like an LCD or a laser or UV pure polymer that is also a conductive polymer?
We are actually, we stay away from any of the actual ink and materials development. So, maybe I didn't mention this, but I mean, so just like the liquid metal is from that company UES, the stretchable silver is from another company, ACI Materials, and we're kind of somewhat being intentional about that because, I mean, we'd like to be, if we, as you can tell, we're kind of more on the application side of things. This is not very basic research. So we'd like, if this does get picked up, we would like it to be something that can be transitioned quickly without having to worry about the ink supply chain. So we're
I don't
not,
know if that material even exists or
yeah.
if it could exist, but I mean, you look at what
Yeah,
an SLS type of 3D printer can do. And
right.
what could that maybe offer you for these types of applications?
Yeah.
I'm not sure.
Good point. Right.
Thank you.
Thank you. Thank you.
Thank you.
Who's in charge? We have a transition plan?
Hey, Jim.
We don't have a transition plan at this point. We're awkward professors now.
Yeah.
I can tell you the color of your shoe. Okay, that's good.
Yeah, I just want to, I won't take as long as the teachers, I promise. Thank you everybody for coming out. Thanks for Doug and.
You haven't done a lot of.
Yeah.
All of those.
Most of you guys are up. Yeah, I know, it's too bad. Most of you guys are up, guys. I'm asking people in the room know that in 12 days, we'll have the 50th IMAP New England Symposium. It's a great technical program coming up. We have an entire session on photonics. So you guys, the often you guys in the room will probably find it pretty interesting. This is the keynote. The keynote is Mark Halfman, and it's going to be about ChipSnet. So that might be interesting to us too. So Mark is acting director of the New England Microphotonics. Oh, he's the acting. So May 7th in Foxborough. Fantastic program. We'll feed you breakfast and lunch. There's be drink tickets too.
Well, this one was
That was last year's. But yeah, so we, if you're interested at all, we'd love to have you. You can reach out to me for more information. Our website is imapsne.org, and my contact information is on there, so you can check it out. We don't have a next meeting scheduled yet. We're working on that. I think Will's in the same mode. So yeah. Other than that, that's really all I got to say at the moment. I did create a couple of photo opportunities for us. So yeah,
So by the way, the symposium is an excellent event.
yeah, symposium.
Really believe you'll come back having met people who you'll be impressed with.
Oh, one more thing too, about the symposium. Rumor has it last year, any student presenter that did either a paper or a poster presentation walked away with the cash prize. So it's like $100. And there's a good chance that this year we'll have the same cash prize. So if anybody's in the room that happens to be a student and might be interested in doing the, if you already have something to present, it's pretty easy to win. Take a quick $100. Just a thought.
And anybody tonight, Matt said he's gonna double it.
I won't hold you.
Yeah, I know.
He's taking care of that.
I gotta go.
Maybe we could get Will and you three and me up here for a group. Yeah, just want to say thank you guys for hosting it and for having us. It's been a great event, and we appreciate
Thank you for making the trip. Now it's now actually west of this, because it's kind of nice to do this, so it's great to have a great audience. Was there something that resonated kind of more in particular, or questions you have for any of us on kind of some of the technology work, some of the national initiatives, some of the workforce development work? Thoughts, comments about things that we didn't answer along the way?
Could you maybe give the big picture overview, which is broadly or?
Sure, so,
He's got it down full.
Starting with the big bang.
so this was.
Oh, that would be me.
Go for it then. So, LEAP is the Lab for Education Applications Prototypes. So this was, the equipment in here was funded by a $4 million grant from the Massachusetts Manufacturing Innovation Initiative underneath the Mass Tech Collaborative umbrella. So it supports the
It's also
on-road.
doing the CHIPS Act, right? What is that? Also doing the CHIPS.
Correct. So it supports us kind of the technology and workforce development on roads to support AIM Photonics, which is the Integrated Photonics Manufacturing USA Institute in Albany, New York. So we are interdisciplinary in nature, as kind of a cross section of physics and mechanical engineering and math, with connections into chemical engineering, computer science, electrical engineering, robotics. So there's kind of a whole broad cross section of students and faculty with projects funded by industry, funded from the feds, funded from states, to support some of these initiatives. So we've kind of been at this for the last 5 years.
There's also a network, so Bridgewater State, Stonehill College, Western New England University, MIT, Springfield. And so they've kind of try to create regional areas, but each one of them has their own flavor, right? We each do something a little bit different, and the engagement's a little bit different in each case too.
Well, I have a question. Back in the eighties, there was an effort to create, the United States is starting to lose its dominance in DRAM production to Asia. So there was an effort to create an Austin. I think it was called Semitech.
Yeah.
But the focus at that time, Semitech, was to encourage U.S. equipment manufacturers to build new state-of-the-art. Is there something, is CHIPS design?
CHIPS Act is that.
Is that, but is the focus to develop next generation production equipment, products? What is the?
It's kind of everything, so it's the materials and
What
the
is the
boundary.
final focus? Is that it's gonna kind of get all of them.
Well, the Manufacturing USA Institutes pick certain sectors, additive manufacturing, integrated photonics, and so they're looking, and there's 17 of these now, I think.
17 now.
And the CHIPS Act is gonna be one of them too, in its own special way. But it's to be at the leading edge of a new technology, to keep it in the States, and then co-develop the workforce along with it. And so there's, bioengineering tissue or growing organs. I'd like to, being a physicist, I call it that. And a lot of different ones like that. And so it's somewhat, yeah. And then each one of these is a different level of investment needed, right? So NextFlex is a little bit more, it could be localized, whereas AIM Photonics needs a foundry, right? It's a $20 billion foundry. But then we're created to help the regional on-ramp, right? So you don't have to go to SUNY Albany to do it there. And then we work with Spark Photonics, who does the PIC designs. We can test it here. And then we have other things like that. So it's meant to be like an on-ramp. And that was the idea of the LEAPs and the M2I2s for that particular Manufacturing USA Institute. But yeah, all of them are designed to bring high-tech manufacturing back to the States.
And then through the CHIPS Act, there are 7 regional hubs across the US. So the New England Microelectronics Coalition represents one of the 7 hubs. So within that, it's kind of a cross section of startups, large companies, universities, government, federal labs, kind of playing in that space for chip security, cybersecurity, electronic warfare, applications kind of on the edge as well. So there's a lot of kind of materials development, systems development. So there's federal dollars, there's state dollars through the NEMC. And Mark will get into that with a lot more detail there.
Yeah, I think there's like 7 areas and New England went broad. So I think 5 of the 7 they have covered, so they try to do a little bit of everything versus picking one particular like cybersecurity. We have folks in ECE doing hardware cybersecurity that with some really cool technologies. And so I think we were in 5 different, it was quite funny, I call it a frenzy at this point because it was the first wave. It's an absolute frenzy, so we kind of stepped back. But there's gonna be several more waves. But the Massachusetts one has a lot of different fields it's playing in.
So I think we're kind of more lab to fab rather than kind of full-on commercial devices. We're not going to compete with an Intel or a Micron, but given the connections between MIT Lincoln Labs, the BAEs, the Raytheon, with kind of the connections to universities and startups, that's kind of the sweet spot that we're playing in right now. Does that answer your question?
Still learning.
Okay.
I'm still learning.
Taking a picture.
Oh, yeah.
We have some other. That's. Yeah. No, yeah, I really don't know. Yeah, hold on. They're not paying.
Oh, you gotta say that. You're right.
Anyway, so get out of the way. All right.
Yeah, you're in the center one.
Smile.
Yeah.